have you ever been driving down a really dark road and just wondered how a simple street sign can suddenly blaze to life in your headlights? Or maybe you've caught a cat's eyes in the dark, and they seem to glow with this weird, eerie light. Well, it turns out the answers to both are connected by this hidden science that is, quite literally, all around us.
So yeah, let's start with that puzzle. What on earth could a cat's glowing eyes possibly have in common with a stop sign? I know, it sounds like a bad riddle, but the answer tells this incredible story about how we've engineered our entire world around the very specific, kind of quirky ways our own bodies work.
Because, this isn't some kind of magic. It's a story of biology bumping right into engineering. It's all about the unique features of the human eye and the totally clever inventions we've designed to work with them, not against them.
Okay, so to really get this, we have to start with our own eyes, because you don't just have one way of seeing things. You basically have two completely different visual systems built right in. You've got a day mode and you've got a night mode.
So let's meet the hardware. On one side, you've got your cone cells. Think of these as your high-definition 4K color camera. They give you all that sharp detail and vibrant color, but, and this is a big but, they need a ton of light to work properly. Then you've got your rod cells. These are your grainy, black and white, night vision goggles. They can't see color to save their lives, but they are incredibly sensitive to even the faintest little glimmer of light.
So how does that switch to night vision actually happen? Let's dive into how those night vision goggles, your rod cells, actually power up when all the lights go out.
The secret ingredient here is a chemical called rhodopsin. It's this light-sensitive pigment that starts to build up in your rod cells when you're sitting in the dark. The more rhodopsin you get, the more sensitive your eyes become. Now, when even a single photon of light hits a rhodopsin molecule, it basically breaks down, and that action triggers a nerve impulse to your brain. And boom, that's you seeing in the dark.
And check out this graph of dark adaptation. It shows the whole process perfectly. You see that first little curve that drops down? That's your cone cells. They adapt pretty fast, but they don't get all that sensitive. But then, look at that second, much deeper curve. Those are your rods. Now, it takes them a good 30 to 45 minutes to fully build up all their rhodopsin, but when they do, wow, your vision becomes literally thousands of times more sensitive than it was before. So here is the crucial point. What if you need to see something, like a map or a gauge, in the dark, but you don't want to destroy all that precious rhodopsin you just spent a half hour building up? Well, it turns out that rhodopsin is pretty much blind to red light. Its long wavelength just doesn't have the right energy to set off the chemical reaction. And that one little biological fact, that's the key to everything.
Which brings us right to our first piece of the puzzle, the stop sign. An object you and I see every single day, whose design is directly tied to the biology we were just talking about.
But wait a minute, here's a little historical twist for you. If red is the universal color for stop, a color our night vision can conveniently ignore, then why in the world were the very first stop signs yellow?
What's so fascinating here is the timeline. The first stop signs that showed up back in 1915 were yellow. And yellow stayed the standard for decades. It wasn't until 1954 that things started to change. And that was all thanks to a brand new technology, a fade-resistant red enamel. It was only after that, in 1966, that red became the mandatory color we all know today.
So the answer to our little puzzle is actually pretty simple. The problem wasn't the idea, it was the technology. The engineers knew red was the right color, but the early red dyes and pigments they just couldn't handle the constant beating from the sun and the weather. They'd fade to a sad pink or even white in just a couple of years. Yellow was a compromise. It was the most visible, most durable color they had at the time.
Okay, so we've solved the mystery of the color, but what about that glow? Why do signs seem to light up when our headlights hit them?
Well, that brings us to the other half of our story, the secret of reflection. Now, this isn't just any old reflection, like you'd get from a mirror or a white wall. This is a very special kind of reflection called retroreflection. A retroreflector is this amazing thing that grabs incoming light and bounces it directly back to where it came from, with almost zero scattering. And that's why the sign seems so intensely bright to you, the driver, because you're sitting right next to the light source, your headlights.
So how does it do that? It's genius, really. Many road signs use millions of microscopic prisms called corner reflectors. It's a beautifully simple idea. A ray of light comes in and hits the first of three surfaces that are all set at perfect 90-degree angles to each other, just like the inside corner of a box. The light bounces from that first surface to the second, and from the second to the third. And after those three perfect bounces, its path is exactly reversed.
And this brings us right back to our original question about the cat.
The inventor of the first retroreflective road markers, a guy named Percy Shaw, he got his inspiration from watching a cat on the side of the road one night. The way its eyes seemed to shine light right back at him gave him the idea for his invention, which he called, you guessed it, the cat's eye. The cat's eye actually has this reflective layer behind its retina. It's called the tapetum lucidum, and it acts like a perfect, natural retroreflector.
You know, once you know what retroreflection is, you start seeing it absolutely everywhere. It's in our road signs, our safety vests, on every bicycle reflector. It's even used in really high-tech stuff like tracking satellites and surveying. It's just a fundamental tool for being seen in the dark. Okay, so let's bring this all home. We've looked at the biology of our eyes, we've looked at the physics of light. Now let's see the brilliant system that we've built by smashing those two things together.
When you put it all together, what you get is a set of rules for staying safe at night, and they're all based on our own biology. So, Rule 1. Use red for stop because it grabs the attention of our color-seeing cone cells, but it doesn't blind our super-sensitive night vision rod cells. Rule 2. Use unique shapes like the octagon so you know what a sign means even if it's covered in snow. And Rule 3. Use retroreflectors so our own headlights become the tool that makes the world around us visible.
And if you're wondering just how precise this technology is, well, the Apollo astronauts left corner reflectors on the surface of the moon. Decades later, scientists here on Earth can fire a laser at them, and every few seconds, they get a single photon back. That's how well this works, over a distance of almost 250,000 miles. It's mind-blowing.
So really, the big takeaway is this. From the color of a stop sign to the reflectors on a cyclist's jacket, our entire system for getting around at night is this invisible, incredible marvel of engineering. And it's built specifically to work in harmony with the biological quirks of the human eye.
It just goes to show you the power of looking inward, right? We've engineered our roads, our clothes, even our missions to the moon, all based on how our eyes work. It really makes you wonder, what's the next amazing innovation just waiting to be discovered, not in some high-tech lab, but just by understanding ourselves a little bit better?